Hello, students. Today we will discuss with three topics here. The first topic that I want to discuss uh, in this particular class is regarding the bit and power allocation in multi-carrier modulation here. And the second topic which I wanted to discuss is regarding the peak to average ratio. It is nothing but here PAR in multi-carrier modulation. And the last topic which I wanted to discuss is channel coding in multi-carrier modulation here. Okay, let me begin with first topic, that is bit and power allocation in multi-carrier modulation here. Now, what is exactly what you can say that the understanding of this bit and power allocation in multi-carrier modulation here comes into picture. So we try to optimize the performance of multi-carrier system here. Okay, using this power and bit allocation procedure here. Okay, that too for a multi-carrier system which is been transmitted over a linear time invariant channel here. Plus, there is an addition of what you can say that additive white Gaussian noise here. In that scenario, we wanted to increase the performance of the multi-carrier system here. Okay, with the help of bit and power allocation here. Okay, so there are, as you can see in the particular PDF here. Okay, so there are n sub channels are there here, or you can say sub carriers are there here. Okay, and each subcarrier is being modulated with the help of the modulation technique called as a quadrature amplitude modulation here, where m is equal to or mi is equal to 2 raised to bi here. Okay, so m represents the number of what you can say that message here. M is nothing but here the message here. Okay, there are number of messages to be transmitted here. Okay, here bi represents the number of bits here. Mi is equal to 2 raised to bi is there, right? Okay, so that nothing but here bi is nothing but here number of bits transmitted here on the ith subcarrier here in the frame interval of t, that is capital T seconds here. Okay, now for example, if you consider that bi, okay, bi is nothing but here number of bits here, right? So bi is equal to in one of the channel here, right? One channel, let us consider I is equal to 1. Okay, so b1 is equal to, let us assume that we are having only 2 bits here. Okay, so b1 is equal to 2, that is nothing but here m1 is equal to 2 raised to what you can say that 2 here, that is nothing but here 4. Okay, 4 messages will be there for m1 here, that is nothing but here for one what you can say that sub channel here, that is for first sub channel here we'll be having 4 messages here. Okay, using the 2 bits here, I think it is quite easier to understand here. 00011011, these are the 4 messages are there here in one of the what you can say the ith subcarrier channel here for the frame interval of how much here, capital T seconds here. Now at this kind of a channel, or you can say the ith subcarrier here, what is exactly the total bit rate here? Okay, that has been given by this equation here. What is that equation? Equation is RB is equal to 1 divided by capital T. Okay, summation of I is equal to 1 to n bi here. I to 1 I 1 to n is nothing but here number of subcarriers or subchannels you consider here. Okay, bi is nothing but here bits here, right? How much is the power that has been allocated in each of the what you can say that ith subcarrier here, that is represented by pi here. Okay, pi is nothing but here the power allocated in each of the ith subcarrier is considered here. What about the total power here? I think it is quite easier to understand. It is capital P is equal to summation of I is equal to 1 to capital N pi would give us the total power that has been transmitted. Now, what is the thing here is, so if at all we have whatever the sub channel is there, right? Sub channel is having what you can say that the bandwidth is sufficient here, or you can say that the bandwidth is very narrow here. Whatever the sub channel we are considering at this moment, Okay, that subchannel is having what you can say that normal bandwidth will be there here. Okay, so if that is a normal bandwidth is there, then whatever the gain we are going to get from this particular what I can say that subchannel here, that is equal to c of fi here. Okay, c into bracket of fi, and which is going to be constant here across the what you can say that frequency band in the particular ith subchannel here. Okay, what is understanding here? If at all we consider the whatever the subchannel we are having here, it is having a bandwidth which is narrower in nature here. And and if at all we consider that the gain of the particular channel is constant. Okay, is constant, it is considered as having a complex value, then we can consider it is having a constant value across the frequency band here. Okay, now what is exactly our objective in this particular topic here? Our objective is to enhance, or you can say that maximize the bit rate here. Okay, for whatever the specified error probability is there here across all the subchannels here. It is not we are just going to look into one subchannel here. Then we need to look into all the subchannels here from 1 to capital N subchannels here. Okay, so to maximize the bit rate here, right? Okay, now whatever the availability of productive error is there here. Okay, now the symbol error probability for the quadrature amplitude modulation at lower rates here. Okay, lower error rates here is given by this particular expression here. P is equal to 4q of root of 3pi. Okay, 3pi and modulus of ci divided by n naught m naught. Okay, there is a square over the ci here. Okay, so this is what is the probability of error. Standard equation has been given at this moment here. Okay, symbol error probability for the quadrature amplitude modulation here, that too at a lower rates here. Now now, what is the CI here? CI is nothing but where PE is the desired symbol error probability, and the CI is equal to whatever the channel gain is there that we have written here. Okay. Now, now what is going to happen here is that we need to so what we have to do here is, if we have to what we have to do here is, like whichever the sub channel is there here. Okay, so if it is able to carry, or if it is able to support at least whatever the messages we are having here. For example, we have considered the b1 is equal to 2 here, right? That means 2 bits we have considered here. 2 bits means what here? M1 is equal to 4 messages are there here. So whatever the sub channel is there here, it should be in a position to support, okay, or transmit, okay, the messages here. Okay, if the particular sub channel is not in the position here, then that particular sub channel will be deleted here, or you can say that the sub carriers in that particular sub channel will be deleted here. Okay, that is what we do here. Now what we do here, whatever the remaining sub channels are there here, where sub carriers are there here, okay, which are which have the ability to transmit that M1, that is nothing but here 4 messages they are able to send. For all those sub channels here, the power will be allocated equally here. Okay, so that it could satisfy the desired error probability here. Okay, this is what is how exactly our power will be allocated here based on the bit selection also here. Okay, okay, now if at all this condition holds good here, whenever there is a what you can sufficient narrow bandwidth is there here, right? Now let us consider that if this that narrow bandwidth whichever we have considered here, if we have a large bandwidth for the sub channels here, what is going to happen here? Okay, whatever this procedure we have discussed just now here, how exactly bits will be there. Okay, if the particular subchannel is having the efficiency to transmit those messages here, then only the power will be allocated here, right? Sorry, this simple allocation of power and whatever the bit is there. Okay, If the subchannel is very large here, then this may result in the loss in the rate here. That means our bit rate would be reduced here at this moment if the subchannel is very large here. Okay, then if at all we didn't get the desired symbol error probability here, we need to utilize the, what you can say that, quantization process here, either to round up for the upper, what you can say that, power of 2 or lower power of 2 here, right? Either we need to round up here or truncate it. If at all we are not able to have the desired error probability here, quantization process should be utilized in this case here. Okay, for each of the messages here. Now the power allocation procedure is usually performed sequentially here. Okay, from one subchannel to the another subchannel, that is I to capital N here, right? Okay, having the largest, what you can say that, where at each step remaining power is allocated equally among the remaining subchannels here. This is how the total power allocation is kept constant here. Remember, every subchannel will be having the equal power here. Okay, okay, now this is how we can explain regarding the bit power, bit rate, and or you can say bit and power allocation in multi-carrier modulation here. There is another two statements are there, which I'm just let you know. Okay, so if at all we measure the signal to noise ratio here, we'll measure the signal to noise ratio for each of the subchannel here. Okay, that to at the receiver side here, and we will measure the that signal to noise ratio, and will communicate the same information to the transmitter also here, so that, okay, so that the transmitter can select the proper quadrature amplitude modulation constellation here. Okay, or you can say that the number of bits should be, per symbol should be selected correctly here, so that we could achieve the desired probability of error here in each of the subchannel here. Okay, there is something called as a DMT here. DMT is nothing but here, the use of the OFDM here, that is of orthogonal frequency division multiplication with a variable size QAM signal constellation for each of the subcarrier is called as discrete multi-tone modulation here. Okay, I hope that bit and power allocation for multi-carrier modulation is clear here. Now let us move on to the next topic here, that is nothing but here peak to average ratio here. Okay, what is this peak to average ratio here? Okay, now whenever there are, what you can say that, uh, n number of signals are there in various subchannels here, what they do here is they add constructively in phase here. Okay, so because of the signals adding constructively, what is going to happen is the peak will be more, large peak signals will occur here. Okay, in the transmitted signal here. So what is going to happen here is that there is result in the clipping of the signal voltage here when we try to pass this kind of an large peak signals to the digital to analog converter here. Okay, so when the multi-carrier signal is synthesized digitally here, and or it may saturate the power amplifier and thus cause what is called as the intermodulation distortion in the transmitted signal here. Now there will be a multi-carrier signals will be there here, right? Okay, so if it has been synthesized digitally, okay, so what is going to happen here is that power may saturate here. I mean, what is good, power will be distributed here, right? Saturate. Okay, so what is going to happen? There is something called as the intermodulation distortion is being transmitted here. Now we need to reduce this particular intermodulation distortion here. Okay. Now to avoid this particular intermodulation distortion here, what we are going to do here is we need to reduce the power that is being given to the transmitter here, or you can say that we need to reduce the power that is being given to the transmitted signal here, and thus we need to operate the power amplifier at the transmitter in the linear operating range. That means within the limited operating range we need to operate the transmitter here. Okay, so this power reduction, or you can say the power back off here, what is going to happen here is this results in an inefficient working of the communication system here, or you can say inefficient operation of the communication system here. Okay, right. Now there are various methods are been devised here to reduce the PAR in multi-carrier modulation here, peak to average ratio here. So one of the best method is, what we can do here is, we need to introduce what you can say the phase shift in each of the subcarriers here. So, and these phase shifts can be selected pseudo randomly here, okay, or by means of some algorithm here, so that our peak to average ratio will be reduced. So this is the one method here. Now another method is, we can we can take one small subset of the what you can say subcarriers here, small set of the subcarriers here, and those small subset of the subcarriers with dummy signals have been modulated here. Okay, and they will be selected to reduce the PAR here. Okay, this is the another method of what you can say that peak to average ratio can be reduced here. Okay, some small subset of the subcarriers will be taken into consideration with the dummy symbols here. Those two will be modulated here, which are selected to reduce the PR here. Okay, now these are the two methods are there here to what I can say reduce the PR here. Okay, so in a digitally synthesized multi-carrier signal here, PR, that is peak to average ratio, may be kept within the specified limit here by clipping the signal at the digital terminal converter. The clipping generally distorts the signal at the transmitter and hence degrades the performance of the receiver here. So in multi-carrier signaling here, what is going to happen again? If at all we don't keep the PR within the whatever the specified limit is there, or within the envelope detector you can consider here. Okay, within the envelope, if you keep it the signal, then there will be no clipping here. If there is a clipping here, then obviously our signal at the transmitter gets distorted here, and hence there is a reduction in the performance at the receiver side here. Okay, this is how we can understand from the point of a PAR, that is multi-carrier PAR in multi-carrier modulation here. The last topic we'll discuss here, which is very short here, that is the channel coding in multi-carrier modulation. What is this channel coding in multi-carrier modulation here? Very simple one to understand here. Okay, so what is it now? You can, before getting into this one here, just let me understand what is exactly the channel coding here. Okay, I think you might have learned in the ECC here. Okay, error control coding here. Okay, nothing but it is a process of what you can say, detect and correct the errors here. Okay, process of detecting and correcting the errors in digital communication systems here. Okay, this particular channel coding is also known as FECC here. FECC means forward error correcting coding here. Sorry, control coding here. Okay, so there may be errors here that are going to happen during the transmission here, right? For example, there may be a noise here, there may be interference here, there may be a fading here. Okay, during the transmission, these three can happen here. Okay, that's why there is an introduction of the error here. We need to detect the error and correct the errors here. That is nothing but here channel coding here. Okay, so in single carrier systems here, what is going to happen? In multi-carrier system, what is going to happen here, right? In single carrier system, what is going to happen? Channel coding is done in the time domain here. Okay, so coded bits or whatever the symbols are there here, they span in multiple signal or a symbol interval here. Okay, so in multi-carrier system, what is going to happen? Okay, in multi-carrier system, usually the frequency domain what does it does here is, it provides an additional dimension here in which channel coding can be applied, so that it is humane to the noise here and other interference also here. Okay, so noise can be reduced in this case here. Okay, one possible channel coding approach is to encode the information bit here on each subcarrier here, okay, separately here, using either the block code or the convolution code here, by employing the trellis coded modulation here. Either you can employ block code or you can employ convolution code, or you can employ the trellis coded modulation technique here. Okay, so this is one of the channel coding approach here. Okay, that should be done in each of the subcarriers separately here. Okay, now there are certain disadvantages that are related to this channel coding here in multi-carrier modulation. One is channel coding in multi-carrier modulation. What is going to happen is there is increase in the complexity here. Complexity will be increased here while encoding and decoding, because n number of parallel channels are involved at the transmitter side and at the receiver side also here. And one more second disadvantage is latency. Latency is nothing but delay here. Okay, delay in the decoding of the data, that too from the n subcarrier channels over the multiple frames here, right? So there are two disadvantages associated with this channel coding in multi-carrier modulation. Then one is complexity, and another one is a delay, or you can say latency here. Hmm. Okay, this is how I could explain regarding the channel coding in multi-carrier modulation here. I hope it is very clear with the three topics here. Thank you.